Okay, so the next thing we're going to talk about is semaphores. Now, we've got a lot of experience with semaphores at this point, but we haven't really talked about them formally. So what we're going to do is we're going to talk about how semaphores help to enable multiple threads to control or coordinate access to a limited number of shared resources. That's the typical use case of a semaphore. Now, semaphores go back a really, really long way. And the reason that they have the name semaphore actually comes from their original usage. And they used to be used as signaling flags, as a way to indicate people either over great distances, like on mountaintops, or they would use them when you had a shared resource as flags. So they had flag like stop and clear, or stop and go, or wait until you can go and then go. The place this is most notably used, it's actually probably still used today in the United States, certainly used in a lot of other countries with a lot of trains, like in India, for example. They're used to control access to a shared railroad track. So when people used to travel a lot by rail, you would have a shared track. You'd have to be single tracking stuff. If you ever ride on a metro system like the metro in DC, and every once in a while the tracks get all screwed up, so they have to single track. Use semaphores to know if you have to stop or go. There's a whole discussion about railway semaphore signaling. So this is the original motivation for using semaphores. Concurrent programs use them to synchronize interactions between multiple threads. So, for example, here's a picture from our Palantir Manager program, where we have a limited number of Palantir and a larger number of beings that want to access the Palantir. And you can go and read more about semaphore here at this link. Typically, you use a semaphore to limit the number of resources that are devoted to a particular task. So even though you might have 100 threads running, you probably have a smaller number of actual resources, like cores, and you want to limit the number of threads and their access to the cores. In fact, that's actually a pretty good example. So let's take a look at an example along those lines. Let's imagine we want to write some kind of image rendering software. In fact, I have that kind of stuff here when I produce these videos after class on my laptop. I go ahead and run a program that converts the films into an MP4 file. And I can control the number of cores I want to dedicate to that, because I have 4 cores on my machine. Now, if I'm just doing nothing else, or I'm using my other laptop, I'll crank up all 4 cores, go to town, sucks up all the processing capability on the machine. If I'm also there, though, trying to use the machine to do email or browse the web or whatever, I probably don't want to use all the cores for image processing. I want to use 2 of them or 3 of them. I want to leave another core for something else. So I might want to restrict the number of things it would have access. So imagine we wanted to have something like that, and we might say we want to bound the number of threads that can run at a time to some number, like 2. So in this particular case, we've got 4 cores, but we're going to have a semaphore with a count of 2, and the thread needs to acquire a permit before the thread can actually run. So the first thread comes along, it acquires the permit, the count goes to 1. Second thread comes along, it acquires the permit, the count goes to 0. At that point, some threads are processing, doing their thing. And any other threads that come along that try to acquire permits, they're going to have to wait. They're going to block. So here we're doing it for image processing. Before we were doing it for gazing at Palantir. Same basic idea. We have more threads that want to do work than we have resources for them to work upon. Once a permit is returned back to the semaphore by incrementing its count, by releasing it, then another thread can go ahead and run. This particular example illustrates full bracketing between acquire and release. So in this case, a thread that acquires the semaphore is also going to release it. But that's not necessary. There's lots of other use cases. We'll look at one in a minute in the examples where you can actually have one thread acquire and a different thread release. That's one of the things that makes semaphores different from reentrant locks and synchronized blocks and stamp locks and all the other stuff we've talked about so far. You can have different threads acquire than release. There are 2 types of semaphores. Counting semaphores, like what we were just looking at, where you have a count. You can have an arbitrary resource count. We'd use the count of 2 for our image rendering application, which means that 2 threads can be going at a time. And then there's also binary semaphores, where you can either be 0 or you can be 1. So those are the only things. You guys will get a chance to play around with binary semaphores for the next programming assignment after the current one. So the current one is the Palantir Manager. The next one is going to be kind of interesting. We're going to implement a ping pong program, which I'll show you next class, because I think we'll run out of time here. But we're going to have a ping pong program that will display ping and pong on your cute computer display. And internally, you're going to implement this using a couple of interesting patterns. And you're going to write basically a semaphore-like mechanism that passes messages back and forth. It's really interesting. So it uses threads with message queues and all kinds of good stuff. So you'll see those later. Human known use of semaphores. So this is one example that I learned this when I was a graduate student in Southern California. We used to go out to a place called Corona del Mar. Here's a picture of Corona del Mar. And this is one reason why everybody took so long to graduate from grad school in California, because you're always at the beach. And the popular thing there to do was to play beach volleyball. So on any given weekend, you'd go down, and maybe there'd be 5 courts or however many courts there were, 10 courts. And there'd always be way more teams that wanted to play beach volleyball than there were available courts. So how do you have a protocol for mediating access to the courts? Well, what we would do is we would have a basket full of beach volleyballs, this kind of thing. And the protocol was whenever teams wanted to play, they would send a representative over to the basket. And if there was a ball in the basket, the team could take the ball and then go play on the court that the ball corresponded to, or any free court, didn't really matter. And when they're done with their game, then they have to come back and put the ball back into the basket. So if there are more courts available than pairs of teams that want to play, there'll be balls in the basket. If there are more pairs of teams than there are courts, then the basket will be empty. And when you go to the basket and the basket's empty, you have to wait until somebody gets done and puts the ball back in the basket. So that's a really nice way to think about keeping track of what a semaphore does. It's a counting semaphore. It's a way of keeping track of a number of things. All right, let's now talk about what Java semaphores do. So Java semaphores are basically an implementation of this concept, and you can read about them here. And they have a class called Semaphore, which you can find the implementation here in Android. And it's basically the same thing as you'd find in Java. And under the hood, the semaphore uses the bridge pattern, just like we always do. We have Semaphore, which has a synchronization base class, which inherits from abstract queued synchronizer. And then it has a fair sync and a non-fair sync and so on. And here's our abstract queued synchronizer. It gets a lot of its methods from that. In fact, in many ways, it works a lot like the reentrant lock, except that you can do things in a more general way, right? You can have other threads release the lock than the one who acquired it, since they don't have to be fully bracketed for a semaphore. And we talked about this before. You can optionally create fair or unfair based on the parameters that are passed in. The other thing you can do is you can give it the initial number of permits, which is sort of akin to how many volleyballs are in the basket to start with, right? So that's what the permit count means. They call them permits as opposed to counts. It's permits. A lot of people get very confused by this. Permits is not the maximum number of things. It's just an initial value. And this is a little hard to get your head around, because if you think about the metaphor with the beach volleyballs, the maximum number of balls in the basket corresponded to the number of courts available. And if somebody came along and surreptitiously threw more volleyballs into the basket, you couldn't really go and play unless you wanted to have 4 teams playing on a court at the same time, which would be very confusing. Although it would be interesting to see. It'd be turned into like a rugby match, right, with a volleyball. So it's not a maximum. The other thing to note is that the value of permits can also be negative. So you can actually initialize a Java semaphore with a permit count that is less than 0, which means it has to be incremented some number of times to get to the point where people can make forward progress. That's a very weird use case, but the main consequence of that is whenever you do a check, you always have to check to see if the permit count is less than or equal to 0 as opposed to equal to 0. Go figure. Here are its key methods. These should look somewhat familiar to you because they're not dissimilar for some of these methods are not all that dissimilar from the ones for locks, but they have a slightly different name and they also have slightly different behavior, which is why they're done the way they are. Notice, by the way, Semaphore does not implement the lock interface because it doesn't implement lock and unlock. It has acquire and and release, which actually is a lot more the way that queued synchronizer works. All right, so here are the methods. Acquire will obtain a permit from the semaphore, and it uses this underlying call that's provided by the abstract queued synchronizer class, and it waits for one thing. And notice it does a shared acquire, because you can actually have multiple things going on at the same time, right? If the count is greater than 1, multiple threads can make progress. It's not an exclusive lock. It does have a count, but it's not an exclusive lock. This thing can be interrupted. Acquire uninterruptibly will not be interrupted, so it just calls acquire shared. This calls acquired shared interruptibly. Try acquire attempts to acquire a lock in a shared manner, and it's got the interesting characteristic, just like the try acquire for reentrant lock, that if it succeeds, it ignores fairness. So what that basically says is if you use try acquire without the timeout values, doesn't matter whether you're in fair mode or unfair mode, if you can get that lock, you're going to get it. So it barges ahead. So don't use this if fairness is important to you. And then release returns one permit. And it does it in a shared way. It doesn't really make a lot of sense in this case, but when we'll see later, release shared, where you give a value of n, you release things, and you can actually have multiple things wake up and start to run. It's perfectly legal for the permit count to exceed the initial permit count. So you could keep saying release, 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 and the count would keep climbing higher and higher. That may be an error at some other level in your code, but the Semaphore doesn't know that. In fact, if you look at the Palantir Manager test program, it actually checks for that. It has logic in there to check to see whether your implementation works properly for your Palantir Manager, whether it'll let it go beyond the number of things that are actually there. Your Semaphore may be happily able to do that, but the Palantir Manager will catch it. There are also a bunch of other variants here as well, and I included them and gave the documentation. Basically, the main thing is, in addition to acquiring and releasing one semaphore at a time, there are also similar methods that are overloaded where you give the number of permits to acquire or release. So you can acquire n permits, or you can release n permits, which is kind of interesting. And then you also have try acquire with timeouts and stuff like that. OK, any questions about what a semaphore does? Now, your simple semaphore that you're doing for what you did for assignment 2A doesn't have the release n property, and it doesn't do try acquire. There's a bunch of things it doesn't really do, but you could. It wouldn't be that hard. Always remember that acquiring and releasing permits doesn't need to be fully bracketed, and we'll see this in our ping pong program that we'll look at later, because the ping thread blocks to get its semaphore, and when it's done, it goes ahead and it releases the other semaphore so it can run, and when it's done, it goes ahead and releases the other semaphore so it can run. So it basically uses binary semaphores to do pinging and ponging back and forth in a coordinated manner. So the thread that acquires the lock is not the same one that releases it. It's the other guy that releases it. All right, let's take a look at how this stuff actually gets used. So this is an example from Android. They have a video editor, which is built into the phone. And you can see the documentation here. And you can see the code here. And there's a class called Video Editor Impl, which implements something called a video editor interface. And you can look here to find all that code. We're just going to look at some of the code, not all of it. So here's the constructor for Video Editor Impl. And it goes ahead and it creates a new semaphore. It's a binary semaphore, which is with a count of 1. And it has the value true. So that means it's fair. So everything that queues up will get released in the order that they waited. We then have methods called lock and unlock, which are really just wrappers around the underlying semaphore try acquire and release methods. So remember, try acquire does a timed acquire fairly, because it doesn't do the non-timed try acquire, which barges, and then release goes ahead and releases one of the waiters. In this case, it would be done in fair order, so the guy who's been waiting the longest. Then there's a method called start preview, which starts to do a preview. And as you can see, if the preview is not in progress, we go ahead and get to be the exclusive owner of this thing. And then we go ahead and we preview. So So there's a bunch of things you do when you preview. You can do overlays, you can do transparency, and other kinds of things, transitions and stuff like that. And then when you're done, somebody calls stop preview. And what stop preview does is if there's a preview in progress, it goes ahead and stops it or sets it to false and unlocks the semaphore so somebody else can go. So what this means is that the long and the short of it is we're using a semaphore to ensure one preview is done at a time, and we're doing the actual processing of the preview off the main thread because we don't want to block the main thread to do image processing stuff on the video. And when we're done, we go ahead and send the results to the UI thread to be displayed. And when the UI thread is done displaying it, it goes ahead and releases the lock. So let's take a look at that code. So that's handled by a video editor activity, which handles requests on a project, overlays, transitions, and so on. And it has a thread called a preview thread, which extends thread. And so the preview thread is, when it starts up, the semaphore is set to 1, which means it's unlocked, right? And so when someone hits the start preview playback button, that will go ahead and run in the background, and it'll process user requests on a project. So it goes in and adds the requests to this queue, and it calls start preview. And that start preview method here, we just saw that goes ahead and locks the semaphore, it decrements it by 1. If it is blocked, in other words, if there's a preview going on, it'll wait its turn in order. And at some point it's done, it gives its result over to the user interface thread. We'll talk about how that works when we get a little further along in the class. And then it goes ahead and it calls stop preview. And stop preview releases the lock so the next guy in line can go ahead and start up. OK, so that's a quick overview of how you do that. Notice that example is not fully bracketed. One thread acquires the semaphore, the background thread, and then the user interface thread releases the semaphore when it's done processing the display of whatever the background thread was doing. So that's how they coordinate. We'll see later how they actually pass information back and forth. It's through a bounded queue. All right, so here's some things to think about. Semaphores are very flexible. So unlike the other kinds of things we saw, they're, so far, acquire and release do not have to be bracketed. So that's a win, right? However, of course, it's also a bit more expensive, or that's actually the Java implementation makes it in the noise as to whether it's expensive or not. Now, here's an interesting thing. You guys are using semaphores for your Palantir Manager stuff, and it's being used to guard access to the Palantirs. But the tricky part here is the semaphore just keeps a count. The semaphore doesn't know which Palantir to hand back. So that has to be handled via some other means. So you have to use some other mechanism to determine which free resource to return. So in particular, in your case, we do that by keeping a data structure, which could be a hash map or a list or a concurrent hash map or whatever you want to use. And that's what actually keeps track of the Palantirs to give back, right? It keeps track whether they're in use or not. But then it uses the semaphore to keep track of how many you can give out. And it uses the blocking features of a semaphore. When the count drops to 0, it blocks the caller, and it has to wait until it gets a chance to run. For many of the same reasons that reentrant lock and reentrant read-write lock and stamp lock were complicated because there's a protocol you have to follow, Semaphore has all the same kind of problems. Now here's an interesting thing. If you look in Android, Semaphore is just about not used at all. In fact, the one example I showed you of the video editor application, I think, is the only example that doesn't come out of the test application. They used semaphores for various kinds of tests to start things up and shut them down. And it's interesting to ask, why is that? Does anybody have a speculation as to why semaphores really aren't that widely used? Well, the answer really comes, I think, to some extent from back over here. It's a pretty low-level means to coordinate things. And as we'll see when we talk about next class's discussion, which we'll talk about condition objects, those give you a lot more expressivity because you can wait for something other than a count to go from 0 to non-zero. which is basically what Semaphore is giving you. It's keeping track of the count of something. So it doesn't really give you a chance to wait on any interesting conditions. So you'll see that condition objects and other stuff are much more powerful because they can let you wait on arbitrary things that you can define, user-defined conditions. All right, real quick thing, we're just about done. This is where the source code resides, at least in Android. You can find similar things in Java. And the nice part about it is that Semaphore is pretty straightforward. The implementation is pretty straightforward. Sync inherits from abstract queued synchronizer. A lot of the work gets done there. There's certain things that get done here in terms of fair and non-fair, but an awful lot of the logic is kind of sucked up into abstract queued synchronizer. In some sense, Semaphore and read-write lock are what abstract queued synchronizer really does well, those kinds of locking protocols. So we'll look at that stuff later. Okay, any questions?